The first way is Newton's method, also known as Newton-Raphson Method. How many of you are already familiar with this method? Oh, a lot of you. Okay, that's great. I'll go over that really quickly then. So we can write this system as a big f of a equal to 0, where f is a nonlinear function. It's an n-dimensional nonlinear function. So f has n inputs and also n outputs, right? Because f actually represents n scalar functions, n multivariate scalar functions, right? Because we have j goes from 1 to n equations, and also I goes from 1 to n variables. So if we write this equal to 0, and we can derive the Jacobian, we define as the partial derivative of f with respect to a. This is called the Jacobian. Okay, it is a square matrix. It is an n by n matrix because f is n-dimensional and a is n-dimensional. In order to find the solution fa equal to 0, we basically need to find the root of this function. And the Newton's method is a way to find the root. In one dimension, the way to find the root of a function, let's say a small f, as a function of a one-dimensional a, okay? The way to find the root of a function is starting from an arbitrary a0. Take the gradient or derivative of this function f. So let's say the slope of this is df dA, okay? And take the value of the function at this point and divide the value by the slope of the function, which gives us the delta A we need to subtract from a0 to get a better estimate. Okay, which means in this case a1 is equal to a0 minus delta A, and this delta A is equal to the reciprocal of df dA times f of a. This is at a0, right? Okay, and of course this goes on, so a of iteration k plus 1 is always equal to a at iteration k minus delta ak, and this delta ak is equal to the reciprocal of the slope of the function times f of ak. Here we are not trying to find the root of a one-dimensional function, but the root of an n-dimensional function. But the Newton's iteration works exactly the same. So here we have an ak plus 1 as a vector, no longer a scalar, is equal to ak minus now the inverse of a Jacobian. Remember here the Jacobian is a matrix. It's a square matrix. So the inverse of an n by n square matrix is an n by n square matrix times the f of ak. Okay, f of ak, remember, is an n-dimensional function, so f of ak is an n-dimensional vector. We have an n by n matrix times an n-dimensional vector. That gives us another n-dimensional vector. So subtract that from ak, we get the better estimate of the root of the function. Okay, so as k goes to infinity, the Newton's method guarantees that if a0 is sufficiently close to the correct solution, okay, then ak converges to the root of the solution. If a0 is sufficiently close to a. In most cases, it's really hard to estimate what a0 is sufficiently close to a. But a good An interesting case is when we are solving a nonlinear differential equation that is time dependent. Then we always know that the previous time step solution is a good estimate of the next time step solution if the time step size is small enough. And in that case, we always have the option, if the Newton's method does not converge, we always have the option to halve the time step size, which means we are getting a better estimate of the initial condition. At some point, we should be able to converge using Newton's method. Any questions on this? The Newton's method is really one of the most useful techniques out there in any kind of numerical analysis. And the second possible approach is not very different from Newton's method. It's so close, it's called the quasi-Newton method. Okay, the quasi-Newton method is a method that works like the Newton's method, except for we don't evaluate the Jacobian exactly. So AK plus 1 is going to be equal to AK minus an approximate Jacobian, let's say JA inverse times F of AK. And again, if the JA is a good enough approximation of the true Jacobian, we could converge. For example, in the previous case, because this matrix actually involves A, if we want to compute the full derivative, so in this case the derivative of A minus B dA, it's pretty complex because we need A of A. That's obviously one component, but we also have a very strange term, that is the derivative of A with respect to A. Okay, that is not a vector, that is not a matrix, that is actually a three-dimensional tensor times A. Okay, so it's a non-trivial thing to compute. But if we somehow know that this term is not as important as this term, or the nonlinearity is not as strong, then we can say, okay, why don't we just take this matrix A as our approximate Jacobian and plug it into this quasi-Newton's method and hopefully converge to a correct solution. The rate of convergence of a quasi-Newton's method is usually not as fast as Newton's method, but potentially the amount of computation involved in deriving the approximate Jacobian can be much less than the amount of calculation you need for computing the full exact Jacobian. So usually, even with more iterations, you still save both computers' time and yourself's time in coding up the exact Jacobian.